Okay, picking up where we left off, let's go ahead and look at direct and diffuse radiation. So, as mentioned at the end of the prior video, when the sun has come through the atmosphere, there are basically two kinds of radiation that will strike a surface, right? So, the two is direct and diffuse. So, the portion of the radiation that has penetrated the atmosphere without having been scattered or absorbed by the atmosphere is in the direction of the zenith angle, and it's termed the direct radiation. I'll cover what zenith angle means later, but it is the direct radiation is what is coming from the sun directly to the surface, right? The scatter radiation is incident from all directions, although its intensity is largest for the directions close to that of the direct radiation. However, because of the radiation intensity is often assumed to be independent of the direction, the radiation is termed diffuse. Basically, there's a portion of the incident radiation that gets scattered through the atmosphere that eventually, when it comes and hits the surface, it hits from all directions. So even if the surface is shaded, there wouldn't be any direct radiation in terms of a shaded surface, but there still would be diffuse radiation. So the total thermal radiation reaching the surface is the sum of the direct and the diffuse. In HVAC applications, we also include a third term, which is reflected radiation. So if I have like a building with a vertical surface, and there's like for example, a reflective blacktop parking lot in front of the building, and it reflects a portion of direct radiation to the building, you would have that third term. So you would have the direct, the diffuse, and then some reflected portion. But in terms of this class, we're going to just concentrate on direct and diffuse. So on a clear day, the diffuse radiation may only account for about 10% of the total, while on a cloudy day, the diffuse essentially accounts for 100% of the total incident radiation because there's normally not any direct radiation on a cloudy day. So looking at emissivity. Emissivity is important because emissivity is a property of a surface that basically quantifies how close to a black body a surface is. So a black body would have emissivity of 1, for example. So as such, the emissivity of a black body would be 1. How do you compute the total emissivity though of the surface? Right. So let's go ahead and talk about that in terms of an example. Here's an example from your book. And it says that for a wall that has a surface temperature of 500 Kelvin has a spectral emissivity as illustrated in the figure below. So spectral emissivity meaning that the emissivity changes as a function of wavelength. So in this particular example, you can see in the graph on the y-axis, you have the spectral emissivity ranging from 0 to 1. And on the x-axis, you have wavelength. And for the first range of wavelength, between a value of 0 and 1.5 microns, you have emissivity of 0.1. From 1.5 microns to 10 microns, emissivity of 0.5. And then from 10 microns and on, you have an emissivity of 0.8. So then if I wanted to compute the total emissive power as a function of that 500 Kelvin temperature, I would first need to find basically what the average emissivity is across all wavelengths. That can be done in a relatively straightforward way by using the function that we were looking at in the prior video, which is looking at the fraction of thermal energy within a certain wavelength range. All right, so if I wanted to find the emissive power, right, the emissive power basically be the emissivity times Stefan-Boltzmann's constant multiplied by temperature to the 4th power. What I need to find is what is the average emissivity across the whole range of wavelengths. So let's go ahead and do that. Again, if I'm going to use those charts, I have here 3 ranges of wavelengths. And I'm going to go ahead and start by looking at this intermediate value wavelengths yield in terms of this thermal energy percentage from the chart. So I'll go ahead and compute lambda 1T and lambda 2T. So the first range ends at 1.5 microns, temperature is 500 Kelvin, and the second range ends at 10 microns, and I'll multiply that also by 500. So I'll get 750 micrometers Kelvin for the first wavelength and 5,000 micrometer Kelvin for the second wavelength. So I get the fractional energy between 0 and the first wavelength to be, according to the chart, if I look it up, 5.9 times 10 to the minus 6. And for this 0 to the second wavelength, I get 0.6336. Again, these are all from the table that we looked at in the prior slide. So I'm going to compute the emissive power. I'm sorry, not the emissive power, but the effective emissivity. Let me go ahead and redraw this to make sure my nomenclature looks the same. I have to take the initial emissivity, right, which again is, in this case, 0.1, between a value of 0 and 1.5 microns. So I'm going to do E1 times the range from 0 to the first range. So that would be that would be 0.1 times that fraction of thermal energy, which is 5.9 times 10 to the minus 6, plus the second range of emissivity is at a value of 0.5. So I'm going to go ahead and put 0.5 times the fraction from 0 to lambda 2. Again, what this ends up getting me is the fraction of the thermal energy between lambda 1 and lambda 2. So I have to take it between 0 and lambda 2 and subtract it from 0 to lambda 1. So in that case, I have 0.6336 minus 5.9 times 10 to the minus 6. And then I add to it the final range emissivity, which is a value of emissivity of 0.8 from basically lambda 2 on, right? So again, that would be lambda, that would be the third emissivity range, and if it's basically if the range is from lambda 2 onwards to the remaining range of the spectrum, I would basically take 1 and subtract out the fraction of thermal energy found between 0 and lambda 2. So it would be 1 minus 0.6336. So that ends up giving me an emissivity of 0.61. And then if I go ahead and if I take that emissivity, multiply it by Stefan-Boltzmann's constant, which is 5.67 times 10 to the minus 8, and I multiply it by the temperature to the 4th power, I can find that my total emissive power is 2,161.4 watts per meter squared. Again, that is trying to find the emissive power based on an object that has the emissivity that changes as a function of wavelength. So let's go ahead and let's move on to looking at irradiation. So what's irradiation? Irradiation is just basically the thermal radiation from the sun incident on the surface. When it hits a surface, a few things happen, right? Some of the thermal energy gets absorbed. Some of it is transmitted through the object, and some of it is reflected, right? So basically the surface properties dictate which one's absorbed, which one's reflected, which is transmitted. Those are done according to three different properties: absorptivity, reflectivity, and transmissivity. Those three constants add up to be 1. Right, so the surface properties, again, absorptivity, which basically defines percentage of the incident thermal radiation that's absorbed by the surface. The reflectivity quantifies the percentage that's reflected, and transmissivity quantifies the percentage that is transmitted through. You add up all those three properties, absorptivity, reflectivity, transmissivity, they should equal 1. So let's go ahead and do a quick example problem. If the spectral absorptivity is equal to the spectral emissivity in example 6.2, i.e. the emissivity equals the absorptivity, and if the irradiation is 750 watts per meter squared, has the spectral characteristics of a black body at 200 K, find the absorptivity, the reflectivity, and the irradiation absorbed if the surface is opaque. Okay, so this problem statement is basically saying the emissivity is equal to the absorptivity of the prior problem, right? So again, this prior problem that we looked at, here we have a range of wavelengths, and it gives you on the y-axis the value of the emissivity based on the range of wavelengths. So what we're going to do in this case is replace each of these emissivities with absorptivity and recalculate the effective absorptivity based on a black body temperature of 2000 Kelvin instead of what this problem had, which was a black body temperature of 500 Kelvin. So that would require us first off to recompute the two lambda t values we had, right? Again, the first range of wavelengths ends at 1.5 microns. Multiply that by a black body temperature of 2000 Kelvin. That gives us 3000 micrometers per Kelvin. And then the second range ends at a value of 10 microns. Then multiplied by 2000 Kelvin gives us a value of 20,000 micrometers per Kelvin. So the value of F between the fraction of thermal energy between 0 and lambda 1 would be, go back to those charts, it should give you a value of 0.273, and the second, the range between 0 and lambda 2 should be 0.9856. So in computing the total effective absorptivity, again, you'd have the first range, which gives you an absorptivity value of 0.1 between a value of 0 and lambda 1, which is 1.5 microns, right? Again, this range between 0 and 1.5 micrometers with a lambda 1 value of 0.1. So that would give us 0.1 multiplied by 0.273. Then I add to that the second range, which is a value absorptivity of 0.5 between a wavelength of 10 microns and 1.5 microns. So basically, I would take the fractional energy between 0 and lambda 2, so 0.9856, minus the range between 0 and lambda 1, which is 0.273. And then finally, the third range, again, which is again, absorptivity of 0.8 between a value of 10 microns and on. So it would add 0.8 multiplied by 1 minus the range between 0 and 0.2, or of lambda 2, which would be 0.9856. That would give us a total absorptivity of 0.395. So that was one thing it was asking for, is the total absorptivity for this black body at 2000 Kelvin that had the same values as emissivity from the prior problem, right? The next part is asking to find the total absorptivity. So again, from the prior slide, it tells us that absorptivity plus transmissivity plus reflectivity equals 1. And since the surface is opaque, the transmissivity must be 0, basically resulting in that the reflectivity would be 1 minus the absorptivity, which in this case would be 0.605. And then finally, the problem's asking is, what is the absorbed solar radiation in that case? Well, in that case, it would just be the absorptivity of, just be the absorptivity alpha, which is 0.39, multiplied by the incident radiation, which is 750. So 0.395 multiplied by 750 would give us a total absorption or absorbed radiation of about 300 watts per meter squared. Okay, hope that example problem helps clear it up a little bit. Now, moving on, just a quick thing to say here: the total absorptivity of any surface is equal to the emissivity under two circumstances. One, when the irradiation corresponds to that of a black body, or when the surface is gray. A gray surface is a surface for which the emissivity equals the absorptivity for all values of wavelength, for all wavelength values. So just to give you an idea of these different, what surfaces have as far as a value for absorptivity, emissivity. This table on the bottom of the slide represents the emissivity and solar absorptivity for different selected surfaces. So the ratio of absorptivity over emissivity is useful for very different engineering parameters, right? In terms of trying to figure out how much something absorbs versus how much something emits. So, for example, aluminum, right, would have a very low absorptivity and a very low emissivity, but Teflon would have, let me look at another one. Absorptivity, for example, black paint would have a high absorptivity and a high emissivity. So, again, especially in HVAC engineering, the color of a window frame, for example, has a huge effect on the amount of energy that thermal energy a building would absorb, mainly because of those characteristics. All right, I'm going to go ahead and end the video here. The next video we're going to get at is going to start looking at the sun's path that it paints through the sky, and how that relates, how that basically equates to how much energy an incident surface would absorb. So at this point, we'll go ahead and stop this particular video.